Okay, this is going to be a quick live stream 30-minute recording going over an HLS block that we have designed for DMA. So first off, we're gonna open it up again so we can go over the interface. So we called it's this stream function. Yeah, so we're gonna edit an IP packager. So we're gonna go over this interface as it opens up. Okay, so let's first go over the files. We have a top level, which has our AXI bus, our stream input bus, and our stream output bus. We combine the clocks on the streams so that it's one clock. We don't need any cross-clocking domain for that. And so we have our AXI interface, our stream interface, and our stream out interface. And we kind of simplify this because we have some expectations. So let's go first into the AXI interface here. So we're going to open up this AXI interface. And we talk about what we changed. So we added an output for this. And this output is connected to the very first register. So basically this interface has 32 registers. And the first register is connected to this add value, mistakenly called add val. And that's outputted back to this kind of top level, as we see here, this add data. Yeah, connect the add value to add data. So next we're going to go look at the input interface. The input interface, so I kind of destroyed what Xilinx did and I added a very simplified one with a few expectations. And basically it's a very dumb interface. It's just adding values every clock cycle and only kind of passes it forward if it's valid. So we have three outputs of this interface, data, last, and valid. Data is our 32 bits of data. Last is at the end of DMA packages, and if required, or the interface will be upset because the package didn't meet the required length. Valid is showing that our data is correct, and this is important if you want to not use things when process invalid data. We don't care. We're just going to process everything, and only the valid data will be sent to the next interface. So we have a very simple interface. We're just saving everything in registers and then passing those values along. Boom. So now we process that data. We have pre-data, pre-valid, pre-last. So reset those registers, and if not, we're going to add pre-data and add value to post-data. Moving forward, we're going to pipeline the last value, pipeline the valid value. And because we expect, because we have no FIFOs in our system, so that means we make a few assumptions. We assume that we can process new data every clock cycle, that we will never need a FIFO on the input. So as soon as we get a value, we can process it. That's a little bit different on the output. If we go to the output values here, where you have the inputs of the last data and valid, we just send it along the pipeline. So this assumes that whatever in the AXI stream pipeline can receive values every single clock cycle. And that may not be true for the DMA engine, so we're going to throw in a stream FIFO in our block diagram to resolve this. Another thing, when we added the associated clocks here, we had to go to the ports and interfaces, and we needed to associate the correct stream A clock to both the output and input streams, so they were working on the same clock. So that's our quick review of the of our HDL interface. So let's go ahead and put it into the block diagram. So it's going to replace this guy right here. So let's go ahead and wipe that guy out. We're going to add IP, and I don't even not remember what it was. It was in the IP catalog. So stream function. So we're going to go add IP. We're going to stream function. Okay. So we're going to take this input. It's not like stream input. Here we go. And what clock? I think they're all running on the same clock again. So AXI clock is going to be there. The AXI reset is going to be there. It's the same clock as everything else, so we can just everything's running on the same clock to make everything easy. But instead of connecting this straight to the DMA, we're going to add in a FIFO. So we go here, we type in FIFO, we'll get an AXI stream Maybe we want a data FIFO. Let me check. That looks right. FIFO depth, memory type, auto, independent clocks. No. Enable packet mode. No, no. That's all auto. That seems good. Let's see what the other FIFO is. So if we add FIFO. So that was an AXI 4 stream. Oh, good. So that was an AXI 4 stream data FIFO. So let's add. I want to see what the other one is. I'm really curious. So go FIFO again. So let's see what the AXI stream FIFO is. This looks much bigger and has registers and changes things about it. Ooh, this seems much more complicated. Oh, does it? I think it converts. That is. I do not know what that does. But we don't need that one. So we're going to delete that. I might look into that later. So we're going to take this outstream, connect it to the FIFO. Take this, connect it to the FIFO. We don't need a 500 value, so let's minimize that to 16 values, right? Seems good. Minimize this because my screen, this is expecting me to have full resolution. I'm not doing that right now so you guys can view this. And clock source, we're going to do everything on the, that way everything is running off the same slow clock. So let's go ahead, put this in line. So now we go DMA, wraps around, goes to stream function, and goes into the data FIFO, and it goes back to the DMA. So let's save that, validate that. While that's validating, let's look at the apparently we can't look at the addresses for this. Okay, while that's going, is not map. Okay, so that's one thing we need to do. We need to go our unmap register here, and we need to right click it, and we want to assign an address. That's the same address we used before, I believe. Do I have the SDK open? Hopefully that's the same address. I don't want to deal with it if it's not. And we'll go and try to see how this works. Okay. We validated, we saved it, right? We saved. Let us generate the bitstream. Okay. That's why it's generating the bitstream. Let's go ahead and launch. Maybe it's after the prepare runs. After prepare runs, we can launch the SDK and verify that everything is set to what we want. Whew. And while we're doing this, we can review the software in the video so that people in the video know how the Microblaze software works. Okay, so we're generating this. Now we can open up maybe I can just open up the SDK. Will it just go to that magical location? So I'll open up the SDK in a separate window, and we'll just point it to the SDK library. So I'll just show you how to do this. We can just look at it. This PC, C drive, up, stream, we're AXI DMA. We're just gonna click there, and that's our folder. Cool, easy to find. Hopefully, I'm not sure our design's going to finish in the time we have left. Apparently that crashed on. Oh, I love it when SDK crashes all the time. So our SDK crashing, let me see if I can fix this real quick by just moving like file SDK. Oh, that's not good. Go back here. I'm trying to see if there's, I guess we could just remove the metadata and force it to open again and just re-add the files. Okay, so let's remove the metadata. Try that. File, launch SDK. So we remove the metadata. See, this allows us to open the SDK. That was kind of annoying because it didn't open earlier. I don't know what's going on. The SDK is still not opening. Okay. Yeah. I'm going to check something in another window. So this is a previous one, I think. This is our, I don't know why this is. Must be another window of it. Okay, so let me just move this to the window we need to. So we do have the SDK, and I don't know where this broken window came from. Just don't save that one, it's okay. We had the project open in 2 separate windows, which is weird. I don't know how that happened. Okay, so we have here, we're just going to import existing projects in workspace, select root directory. Yeah, that sounds cool. Yeah, finish. Okay. Populating, that's great. So launch it on hardware and bring up TerraTerm. Do not find this guy. So let me see if run configurations. Are we not running it on the select? Yeah, run. Oh, okay. So what we need to, I'm forgetting the importance part. We need to program the guy. Program it. Edit clear buffer over here. Okay. So we're over here. We have programmed the board. And now we programmed the FPGA. Now we're going to load the file in. And it works. So let's go through what the code is doing, right? And also make sure this address is correct. Oh, we need to change this address because it's not that address in our HLS port. But let's configure let's talk about what we're doing here. So this is our Microblaze code that is performing the DMA transaction. So first we're initting the platform. Let's go ahead and look at that. And all this is doing is we're enabling the caches and enabling the UART. I mean, we can also take a step in there. Let's just make cacheable regions. Okay. And let's go back. I want to see what init you are. So we're setting the base address of our standard out. Okay. That's interesting. So next we're doing our DMA configure. So this is for our DMA Xilinx core. So we look it up using our X parameter file, and we can find this in the xparameters.h inside the BSP. Under include, we have an xparameter.h, and there's an ID code. We can use this ID code, this parameter, this define value, to initialize a configuration, and this just gives a bunch of general useful information. Then we create our DMA pointer, and now we're going to initialize that pointer using our configuration pointer. And we're going to reset the DMA. We're no longer using these values, so they're not important at the moment, but we can discuss what we're doing here, right here. So the first important thing we're doing is we are writing data. So we're going to write 10 words of data starting at address 800. I just realized something. This should be times 4 because this is byte addressable. So we should have, it should definitely be byte addressable here. We're actually getting our full thing out of it. Yeah. Oh, it's because we cast it as an int. So because we cast it as an int pointer, this is the cool part. So it's because we cast it as an integer pointer, is incrementing by 4 automatically. That's the compiler does that. So we're writing 10 words of F000 to our DDR memory, which starts at an address. Save that. Copy. Next, we're going to configure our HLS core. This is the value we're adding. So we're going to add 100 hex to all the values that go through a core. We're going to verify our reset is done. We'll have an output there. And we're going to begin a transaction. So this is a DMA to device transaction. So from DDR to the FPGA, starting at this address using this many bytes. Then we're going to do a receive transaction to this destination in DDR and say FPGA to DMA or FPGA to DDR of the same amount of bytes. Then we're going to disable the cache in the we're going to disable the cache. Interesting, we disabled it for that location, but we're reading from this location. I feel like this should be 80. Okay, doing some quick changes here. So this disables the caching of those values so we can see the new values in DMA. Because when we do a DMA transaction, our cache table in the Microblaze does not update. So we need to invalidate that range so that the processor will read those values. And then we're going to output the values at the end. And we should get these values plus 100 hex that are incrementing. And as we can see here, we get that. Add 100 and the increment. This is all done in hardware through a DMA transaction. And this is the code for it. So let's go ahead and then we can just rerun it. This one, and we can just set up the tear term, and there you go. It ran again. So once this guy finishes, it failed. That's great. Let's figure out. I don't know why you're unhappy. Okay, it looks like we may need to rerun synthesis because we crashed it. There's 2 project windows going up and it was running through it. Okay, so we got about 10 minutes left. I don't think we have much time. Did I move this guy? I think I moved this guy. So our goal so far, so right now we're learning how to do streaming interfaces, and our goal is we want to do image video processing on this hobby FPGA board. And I'm going to start posting videos of how we can do image processing, high quality image processing. So one of the things I want to do is I'm going to put this real quick. I'm going to put this PMOD DVI converter on the board, and we're going to use that to have an HDMI or DVI over HDMI output. So we can see live. We're going to use video direct memory access to be able to get a video going on this board. and we're going to use the Ethernet right here to be able to send and receive data. So we're going to try to do video processing on here, and then I'll install OpenCV on my computer and try to run it on my CPU and my GPU, and we can compare the speeds of specific transactions and see how well we can perform in one versus the other, and show you that this board right here can achieve better performance than the CPU and GPU I have installed, which are pretty powerful in themselves. And our roadmap right now, let me just open this little sticky note right here, is we're gonna finish this VHDL and we're gonna test it. We're gonna get VDMA working with this PMod because I think that'd be really cool for you guys to see the video. I'm gonna have to point a camera at it, unfortunately, because I don't have a HDMI video capture device at the moment. That might be something to look into. I could easily use an FPGA to do video capturing, which, I mean, unfortunately I don't have another DVI because it'd be funny to do like video capturing of it. I guess we could have the DMA. We could do that. I could have the VDMA broadcast back into itself, and we could save the process data, and I could send it over Ethernet later, but it won't be live unless I can figure out Ethernet to show it. That's a fun project. And then I want to do a sorting HLS where we're going to take an array of values in HLS and sort them and show you how you can do sorting in AXI Stream, but also how that messes with the latency. And we want to guarantee that even though we're sorting the package, that we can process a new one every array size. So like if we're sorting 10 arrays, we want to be able to process a new array of 10 every 10 cycles. And then here's where we're going to start doing some video processing. We're going to do an HLS custom 3x3 kernel. I already have the code for this from previous projects, and we can implement that and show you how we can do a very simple edge detection, outlining, sharpening, stuff like that. And we should figure out how to do erosion dilation sometime. I'm not sure how we can do if you can do it on those kernels. Then we're going to try to do that same 3x3 kernel in VHDL. I feel like we can get much better performance in the VHDL. I'm curious, because when I try to scale up my way I do HLS, this becomes very ugly. But I want to see if I can easily scale it up in VHDL and get some really good performance and low utilization. Yeah. So unfortunately, I don't think this configuration is going to finish in time to show testing. So the next video will show what this device looks like. And since we don't have much else to look at for the moment, I think this might be a good place. Oh, I have been not paying attention to my comments. I feel rude right now. Have you used the Zillibus before? So let's figure out what Zillibus is. It's an FPGA core for easy DMA over PCI. I have not used Zillibus before. I haven't had a device that has PCI connection yet. But that would be a really fun project. I will think about that. I'm looking into let's open it up here. Squirrel Acorn. So I've been looking at this FPGA that does have PCIe, and it'd be interesting to use that core on this device. What board are you guys using? So yeah, so you guys are working with a PCIe right now. I assume you're using Xilinx FPGA because you reference the Zillibus. What board are you targeting? Is it? Do you have a name for the dev board or something like that? Because was it? I've been looking at these boards. Oh, they have a nice website now. That's cool. Xilinx. Go to Amazon. Their Amazon website's so much better. Wow. You got a board off of Alibaba. That seems sketchy. I've never really. That's a cool option. So yeah, for a PCIe one, I've been looking at one of these guys. Let's see the one. It's the one with the Artix on it. Altera Artix 200T. Yeah, I think this is the one I've been looking at. I think you can get a cheaper version without the DA module. If you can just get it by itself. Yeah, so this is the board I've been looking at. It's a little bit more on the pricey side. We're talking about $500. But you found Alibaba. Let's see. I want to see what board you guys got. So FPGA. Let's see what Alibaba has for FPGAs. That's the one I've been interested in. They have it way cheaper on this website. That is a fun price. That has a different processor on it. Yeah, let's look up Xilinx. I want to see what boards we got. Xilinx Zinc. Can I put in Artix? Will it come up with the Artix board? 100T Xilinx FPGA Artix board. Oh, that's a fun one. Yeah, you get some really good prices here. And since you can buy these on Amazon for like 3 times the price. There we go. Wow. This is $500 on Amazon. And then you can get $200 on Alibaba. And this actually has really good documentation. I talked to them, they sent me good documentation for it, and it's really, really good. Yeah. So this board, you can actually, the company has documentation. They actually have a demo, a PCIe video output demo for this board, and they have a Dropbox with a bunch of files, a bunch of useful information, and it's great. For $200, that would be a good price. I like how you can get the module for more. The module itself is more expensive than just the overall board. I wonder if they actually send you the chip as well, or is that not populated? This is an RTX 7 on it. Details. Wow, I'm really tempted to just go at it and get one of these on here. That'd be fun. Is that the drive on the Linux side, on your host computer side? So you're saying the DMA is using the DevMem 8. Is that on the host? That's on the host side, right? Running Linux. Okay. So, and you're saying you used an FPGA, I want to say Intel at this point, Cyclone, um, Cyclone 4. Gotcha. So, are you using one of these boards? Um, let's type in PCIe if something comes up, right? PCIe. That is not. We'll put in Altera. These aren't what we wanted. Let's try again. Yeah, I'm not seeing one off the bat here. Not seeing anything that's PCI capable, but that's cool. I definitely want to get into some PCIe development and try to look at Windows development, making kind of a an integrated accelerator card for my computer that I can easily send data to and from and process information on it. Yeah, nothing PCI pops up, but that's cool. Yeah, if I'm curious to see what board you're running because I've been looking for a PCIe Cyclone board as well, and you say you found a cheap one. But yeah, I'll keep my eye open on this. Alibaba seems interesting. I'm a little sketchy to buy a ton of them from it, but maybe a few would be interesting. Okay, guys, that's going to wrap up our stream for tonight. I will be on tomorrow. I'm not sure if I'm going to be doing FPGA or video games. We'll find out tomorrow. John Hillington, thanks for the conversation. Feel free to come back later, and we can talk more about FPGAs. I'm curious about your PCIe project. Okay, everybody, bye.